morning, students. Today in this video, we are going to prove that every regular space with a countable basis is normal. Okay. We have already discussed that definition of a regular space and some of the properties results. Okay. And suppose we are having a regular space whose topology is induced by a countable basis. Okay. Then the space becomes a normal space. Okay. For the proof, you take X as a regular space. X is a regular space with a countable basis. Say this could be. Okay. With this, we mean that X is a regular space whose topology is induced by the basis B, okay, which is a countable collection. So B is a countable collection. To prove that X is normal, the first condition we need is X basically a T1 space, okay, but that is guaranteed here. Okay, so X is a regular space. Therefore, first of all, it is a T1 space. Therefore, there is no need to prove that separately. X is a T1 space. That is already in the hypothesis. But to prove X is normal, the next condition we have to verify is for each pair of disjoint closed sets A and B, there are disjoint open sets which separates these disjoint closed sets. Okay. Suppose you take arbitrarily A, B as closed sets which are disjoint. We need to identify an open set U containing A and another open set B containing we need to prove that there are open sets U containing A and an open set V containing B which are disjoint. Okay. For that we proceed as follows. Okay. You take a point of A, then definitely X is not a point of B, okay, because A and B are disjoint closed sets, basically. Now here you are having a point and a closure not containing the point. Okay, your X is a regular space. Therefore, by definition, there is a neighborhood, say Ux, and a neighborhood V suffix B, okay, of B, which are disjoint, such that X is in Ux, B subset of V suffix B, and Ux intersection B suffix B is empty. That is, the point X and the set closed set B not containing X can be separated by means of disjoint open sets in X. Now, because Ux intersection BB is empty, okay, this Ux will not intersect B also. This Ux intersection B is empty. So what it means, to each X in A, there is a neighborhood to Ux, okay, containing X, which is disjoint from B, Now recall the result which characterizes the regular space. Okay, a T1 space is said to be regular, a T1 space is regular if and only to each point X and a neighborhood of X. Okay, there is another neighborhood to V such that whose closure is contained in the given neighborhood. Okay, so by the characterization theorem, there is a neighborhood V, okay, of X such that V closure is contained in Ux. There is a neighborhood V of X such that V closure is contained in Ux. Now, script B is a basis. Therefore, that means the topology tau is induced by B. So, from that you can easily say that given any open set containing X, there is a basis element which contains the point and contained in the given set. Therefore, by the definition of basis, there is a basis element, say B, or I can call it as a U. Okay, there is a basis element U of basis element B of there is a basis element U in B such that X is in U contained in V, U contained in V. Therefore, U closure contained in V closure. Therefore, U closure contained in V closure. Okay, your V closure is contained in UX. Your V closure is contained in UX. That UX is designed from B. Therefore, okay, what we can write simply is there is a basis element. There is a basis element. There is a basis element U containing X such that U closure, okay, U closure is designed from B. U closure designed from B. Look at that. That's the way we are getting the basis element for each X in A. Okay. There is UX and VB with this property. UX intersection VB is empty, and therefore UX intersection B is empty. Now, using the definition of characterization of regular space, there is another neighborhood V of X such that V closure is contained in UX. And now, script D is a basis. Therefore, there is a basis element U containing X such that U is subset of V. As we know that U closure contained in V closure and your UX is designed from V. Therefore, this U closure is also designed from V because U closure is subset of V closure. Yeah. Now summarize what you get is for each X in A, there is a basis element U containing X, whose closure is designed from B. If we do this process for each and every point of A, we are getting a collection, okay, a collection of basis element. Okay. Because the basis itself is a countable collection, so you are having a countable collection of, okay, a countable collection of basis element such that each containing the point X and whose closure is designed from B. Whose closure is designed from B. Okay? Because every time, even though you are varying the point over A, okay, there is a basis element in stub B. Stub B is basically a countable collection. Therefore, we are getting a countable collection from B, stub B. Each one contains a point X and UN closure. Each closure is designed from B. As A and B have the same characterization, that is A is closed, B is closed, A and B are designed, we can do this process for B also. Okay. So similarly, there is a countable collection of basis elements, say Bn, okay, such that Y is in Bn and Bn closure is designed from A. Here Y varies over points of P. Okay. Here X varies over points of A. Okay. So we do the same process by taking B as here and A as here. Okay. Now it is clear that your A subset of union of UN and B subset of union of Bn, n equal to 1 to n. That is obvious because if you give X in A, X is a member of some basis element. Okay, therefore X is in UN for some n. Similarly, if you give Y in B, Y is in Vn for some n. Therefore, A is covered by this UNs and B is covered by this Vns. But if we take this union of UN as U and V, union of Vn as V, okay, you may get an open open set containing A and an open set containing B, but we may not sure to say that okay, these two are disjoint. These two are disjoint. Okay. For having such disjoint open set which separates this A and B, we do as follows. Okay. So define for each n. Okay. Let us define un dash as un minus union j equal to 1 to n vj closure. So this is your un dash. Okay, this is your un dash. What are the facts we are having for this un dash? Is basically your un dash is an open set. How? So your un dash is equal to un intersection okay, union j equal to 1 to n vj closure complement. But using the properties of set theory, okay, un intersection, this is again intersection j equal to 1 to n vj closure complement. As we know that closure of any set is closed and therefore its complement is open. Finite intersection of open set is open, therefore this set is an open set, intersect with another open set, therefore overall this is an open set. For each n, your un dash is an open set. Okay. Not only that, this un dash union, okay, un dash union will contains A. Okay, because we give any x in A, okay, x belongs to n for some n, x belongs to. So observe, maybe recall that how you obtain all these un's, x in A, okay, this x belongs to u and not, okay, for some n naught. Because this un collection is actually a cover for your A. Okay. So x belongs to u and naught. Also, these vj's, okay, whose closure is all closure is disjoint from A for every j. We are actually collecting vj's in such manner. Okay, vj closure is disjoint from A. Therefore, vj x not in vj closure for j equal to 1, 2, etc. n naught. Okay. For every j it is true, therefore in particular j from 1 to n naught, x not in vj closure, which means that x is not a point of union of vj closure, j equal to 1 to n naught, but x is in u n naught. Therefore, x belongs to u n naught minus union vj closure, j equal to 1 to n naught. That is your capital U n naught dash. So, if you give the point x in A, okay, it is in u n naught for some n naught, u n naught dash for some n naught dash. Therefore, every point of A lies in some of these u n dash, which means that A is contained in union of u n dash. So similarly, you can define. Another collection of open sets, namely Vn dash. Vn dash is equal to Vn minus union of uj closure j equal to 1 to n. For each n, we define Vn dash. As discussed earlier, Vn dash is also open for each n, and this union of Vn dash actually covers B. Okay, so A will be contained in this union of un dash, and B will be contained in this union of Vn dash. This is true because of our construction of this Vn dash and un dash. You call this as your open set U, and this is an open set V, okay, as the required open sets. So now we already observe that this union of Vn dash is open set, therefore U is open. This union of Vn dash is open, therefore V is open. U containing A, V containing B. Now we claim that U intersection V is empty. These two are the joint sets. These two are the joint sets. Okay. Suppose, okay, there is a point Z is common to this U intersection B. Suppose there is a point Z common to this U intersection B. Then Z is in U as well as Z is in B. Therefore, Z belongs to, because it is in U, it is in, maybe you call this U J dash for some J. Similarly, Z is in B, therefore Z is in this union, therefore Z belongs to a point V J dash. So Z is a point in V K dash, may not be the same index, okay, for some J and K, for some J and K. So here there are two cases, okay, J may be less than or equal to K, or K may be less than or equal to J. You consider first J less than or equal to K. J less than or equal to K. So in this case, okay, you observe Z is a point of Vk dash. Z is a point of Vk dash. That means Z is in Vk minus union I equal to 1 to K Ui closure. The definition of your Vk dash. So Z is in this set means that Z is in Vk, but Z not in this union I equal to 1 to K Ui closure. We are dealing with this case, J less than or equal to K. Okay. This means that Z is not a point of Ui closure for every I between 1 and K. Z is not in Ui closure. Therefore, your J is less than or equal to K means that Z is not in Uj closure also. Because J will be less than or equal to K, it is an index greater than or equal to 1. Therefore, here J satisfies this inequality. 1 less than or equal to J, less than or equal to K, therefore Z is not in Uj closure. So, you have this inside. Now, Z is in Uj dash. Z is in Uj dash. That means Z is in Uj but not in union I equal to 1 to J Pi closure. Anyway, Z is in Uj. Z is in Uj. This means that Z is in Uj. Here Z not in Uj closure. And Uj is subset of Uj closure. So therefore you get a contradiction. Z is a point of Uj but not in Uj closure. You get a contradiction. Therefore this case is not true. Okay, this case will not arise. Suppose K less than or equal to J. Suppose K less than or equal to J. Suppose K is less than or equal to J. Then you consider Z is in Uj dash. That means Uj dash means it is in Uj but not in the union I equal to 1 to J Bi closure. Okay, this is the definition of your Uj dash. So Z in this set means that Z is in Uj but Z not in this union Bi closure I equal to 1 to J. Again as earlier, okay, similarly Z not in Bi closure for every I between 1 and J, and therefore in particular for K. Okay, therefore in particular for K. K is an index between 1 and J. Therefore, Z not in Vk closure. Now Z is in Vk dash means that it is in Vk minus union of Ui closure I equal to 1 to K. So that means Z is already a point of Vk. Now here Z is not in Vk closure. You get Z is a point of Vk. Both will give the contradiction. So we get a contradiction. Therefore, this case is not true. But these two are the only possible cases. So each case you arrive at a contradiction. Therefore, your assumption there is a common point between U and V is wrong. Therefore, U intersection is empty. So summarize what you have proved is for arbitrary closures A and B, there are open sets, okay, U and an open set B which are disjoint, okay, U containing A and B containing B. That means for each pair of disjoint closures, there are disjoint open sets which separates the given disjoint closures. So which proves that your X is a normal space, because we have already proved that X is a T1 space. Now we prove that every pair of disjoint closures can be separated by means of disjoint open sets. Therefore, your space becomes a normal space. I hope you understand this small result. So thank you.